Well, hello everyone, welcome back to Adrian's Digital Basement 2. On a recent video, I was working on this PC XT clone motherboard, and what was happening with this board is, while it used to work perfectly, just started having malfunctions where the RAM does not work reliably. Essentially, the BIOS RAM test and diagnostic ROMs I put in here just report random RAM errors. So we have errors with random bits and random addresses all over the place. And that includes parity errors as well, which kind of indicates that maybe there's something happening where the data is not being written to the RAM correctly. Not really too sure. In the last video, I did a whole bunch of troubleshooting and I came to the conclusion that maybe the bus transceiver, which is this IC right here, had gone bad. This motherboard has suffered corrosion previously from a leaking clock card that was in here, and I thought maybe this chip was the problem, so I swapped it out, and unfortunately that did not remedy the situation. The machine still gets those total random RAM errors even with the new transceiver in place, so I've actually gone ahead and put the old one back on because it was probably totally fine. So in this video I want to try to see, well, if I can figure out what the problem is with this thing, and I have the schematics printed out for the IBM PC XT, the 5160. While this motherboard is slightly different than that, it's really a clone of the original XT. So pretty much everything that's on here is going to be exactly the same on this, with exception of a few things when it comes to the way the ROMs work. And that's because this can use standard EPROMs and there's a bit of configurability on here. So they went and installed a PAL chip right here to handle that logic. The one thing about these schematics though that make it a little bit tricky is that the markings for the chips on here, like U11, U12, U13, do not match what's on this motherboard. So when we look at a chip on there, I have to figure out which is the appropriate chip on this motherboard by checking some of the signals that go to various components. I was able to not use the schematics in the first video to figure out that that was the bus transceiver that connects the RAM to the CPU part of the data bus. And as I said, that didn't fix anything. Now, either in a previous video or just previously, I don't remember if I made a video about it, I ended up replacing this chip right here, which is a latch. It's a 74LS373. And this latch is used for part of the DMA system on this motherboard. And the symptom of this bad chip was when the system was booted up, anytime we tried to access the floppy drives, it would corrupt memory and then crash. Now, this is the IBM XT schematic, and that is the chip that I replaced, the LS373. And it is ICU11 on the actual XT, and on this motherboard, it is marked as U15. So that's what I mentioned about the part numbers not matching. What this chip I replaced does, along with these three other chips, is they allow the DMA controller to drive the address bus. And you'll notice up here we have address 0 through 7, and then here we have 8 through 15, and 16 through 19. That's all the address lines on the IBM PC or the 8088. And when a peripheral or some other device on the motherboard wants to do direct memory access, essentially the CPU goes into a halt state, and then that thing, like the floppy drive controller, is able to write into the DRAM directly. Well, it needs the help of something like this IC right here to control those address lines, because normally that's what the CPU is doing. Well, this thing takes over from the CPU and it is writing directly to memory. Well, I think what had happened is this chip had gone bad, and I have an arrow there just saying that that's the one I replaced. I think it had gone bad and it was not writing to the correct addresses when the floppy controller was instructing the DMA controller to drive the address bus. That had the effect of corrupting the RAM in the system anytime the floppy drive controller was being used. Now, in the IBM PC design, IBM picked DMA channel 0, and there are 4 channels, by the way, 0, 1, 2, and 3. They picked channel 0 to handle the DRAM refresh. So with dynamic RAM, or DRAM, that's on the motherboard, you have to constantly access the memory, which is the refresh function of the RAM, and that keeps the contents of the DRAM alive. There are parts of the circuit inside the DRAM chip that anytime you read part of the DRAM, it essentially refreshes those little capacitors that are storing those zeros and ones inside the chip. If you don't do that, what happens is the contents of your RAM starts to decay. So if you fill up the RAM with, say, all zeros and you don't refresh it, then suddenly those zeros are going to flip to ones and just start to become random garbage. It takes a bit of time, and there's if you look at the data sheets for DRAM, there's specific timing that you need to refresh them at and whatnot to make sure that you don't lose any of those bits. But that's what the DMA channel 0 circuit is doing on the motherboard. And of course, it's using these 3 chips to do that. Now, I mentioned I swapped out this chip already because I think corrosion had gotten to it. It had leaked off that card. But it's possible that these other 2 chips, well, if they're malfunctioning as well, then the DRAM refresh may not be working correctly, and say it might not be refreshing all of DRAM, or maybe it's intermittent, something like that. Now in part one, I had the super soft or landmark or whatever it's called diagnostic ROM installed in this motherboard, and it does do some checks for refresh and slow refresh and stuff like that. And those all passed perfectly. It didn't indicate that there was any kind of issue, but we were still getting those random DRAM errors. So I don't know how good the DRAM refresh test is with that diagnostic ROM, and maybe, you know, it's actually kind of working, but not well enough. And that's why we're getting these random errors. It's not totally clear to me. So let's dig into the schematics a little bit on this thing, and just want to kind of talk about how the general architecture of the system is when it comes to DRAM access. So right here we have the CPU and the numeric coprocessor, or the number processor, whatever you want to call it, NPU or FPU. Notice here that these lines say AD0 through 7, and that's because these are address lines and data bus lines combined. The rest of these lines, A8 through A19, are just normal address lines, but these ones are multiplex. That means that sometimes they're data bus lines going in or out, and sometimes it's address lines, which are all going out. So because of that, any Intel 8088 or 8086 type systems need to have a series of chips over here to generate the address lines and the data lines that go to the rest of the system. So if you look down here, we have those AD lines 0 through 7 going into a bus transceiver, and that generates the data lines D0 through D7 that goes off to various things in the motherboard. And then we have a latch right here that handles those address lines that are multiplex with this. And then we also have a couple other chips that are handling the output of those address lines. That's another latch actually right there. And yeah, what's happening is the CPU sets up the address bus, it gets latched into these chips and then this chip here, and then that goes to the various peripherals on the motherboard, and then it switches over to data bus mode, and then this bus transceiver here is either sending data bus lines out or in, if it's like a read from RAM or a write to RAM, you know, depending on that kind of thing, or a read or write to any other peripheral on the motherboard. So anyways, the way these are called out on the schematic are A0 through A19, and then D0 through D7. Now, these particular data lines don't generally go directly to peripherals. They might go to the IC slots and stuff, but they definitely don't go to the various chips on the motherboard. And case in point, there's this chip over here, which is the 8259, which I don't even know what this does. I guess it's the interrupt controller, actually, looking at that, because we have all the IRQ lines. Well, notice that its data bus lines here are hooked up to the XD set of lines here. Now, these go off to a different sheet. These are not the same as these data bus lines over here. These go through a bus transceiver. In addition, it has one address line that's used here, and that's because this probably has like 2 different registers, and that goes through an XA0 line. So also that is not hooked up directly to the address bus here. Now we can tell over here that these go to various sheets, so sheets 4, 5, and 3, 4, 5, and in fact the data bus lines here go to 5, 6, and 10. So if we go to sheet 5 here, we're going to see the address lines are right here. There are the data lines. And then we have another set of bus transceivers here, LS245s and then 244s, to generate those XA lines. And then these go off to various places on the motherboard. The XA lines go to the ROM chips. Now on this particular version of the motherboard, it's the 256/640K version, there are only 2 ROM chips. Of course, this is different than what we have on here, which has more chips, but you can ignore that particular difference. The data bus lines, the XA ones, are also what are driving the ROM chips, and we're having no issues at all with ROM. So we can be pretty confident that we have no issues at all with this XA set of signals. These are all working perfectly. Now these go off to a whole bunch of other sheets as well, including sheet 1, which was that interrupt controller we saw. And here we are on sheet 9, and this is also those XD signals again, and the XA lines too. And here we are with the ISA bus, and this thing is actually connected directly to the CPU address and data bus line. So it does not go through any bus transceivers, well, other than, if we go back to the first page here, other than these ones right here. But we could be pretty sure the ISA bus works because we're having good VGA or CGA card. I was using a CGA card that was working perfectly. And also we saw that the ROMs were working as well. So it seems like I said, all those XA lines, which, yeah, incidentally, if we kind of look around here, we're going to see more of them. There's some more XA lines here and XA lines there. That stuff all seems to be working. Oh yeah, the DMA controller itself is also talking on these XD and XA lines. So again, we think those are good. Now that brings us to page 6 here. Now this is the DRAM. Here is DRAM on the motherboard. And these are actually connected directly to the data bus lines via a bus transceiver, and that creates the MD lines, which is the memory data bus lines. And this was actually the bus transceiver that I did swap out. And now it's labeled U9 on here, and on the motherboard, it looks like it's labeled U13. That's this one right here. but that was swapped out. And we found that that made no difference whatsoever. Now, the two signals that drive this are the direction signal and an enable signal. The direction signal is this XMR signal, I have it highlighted, and that goes off to another sheet, sheet 5. And then there's also an enable pin, which is this one here, RAM address select, and that comes from sheet 3. Now this goes off and does some other stuff as well, and this has to do with like multiplexing that goes to the address lines, to the RAM chips and stuff like that, which is what's happening right here. These are multiplexers, LS158s. Now this takes the regular address bus signals and then converts them into, well, the multiplex row and column stuff that the DRAM needs. Now for DRAM to work, you need working column and row address select lines, and they go into the DRAM chips, and you can see here that they come from sheet 3. So let's just take a look at sheet 3. So here we are on sheet 3, which also has that RAM address select line, and that comes over here, and that goes into this gate right here at U24 and LS00. So we need to look at that signal, because if that signal is not correct, well, that's going to cause issues with that bus transceiver. So we need to look at the output of that chip. Also, this chip here is clearly used to drive this. Now there's another DAC0 whatever. This is the DMA request signal that comes from the whole DMA circuit, and that goes into this LS138, but it also is part of driving the ROM or RAM address select line. So we definitely need to take a look at that signal, because remember, I mentioned there was issues with that whole DMA circuit with the corrosion. So maybe this is not working correctly. This should always be pulsing when the system is operating, because the DMA should be refreshing the entire DRAM circuit. Now with the rest of the stuff that's happening on here is all the column and address select lines are being generated right here. And it is important that all of these signals are working correctly. Essentially, these are like the chip select lines that go to the DRAM, and they should be refreshing at all times, not only because the CPU is accessing the DRAM all the time, well, most likely, or not always, of course, if it's stuck in ROM, but the DMA refresh circuit is going to have to be accessing the RAM to refresh it, so we should see some activity, at least on some of these lines. I can't remember if it's the column address select lines that should be selecting all the time because of refresh, or if it's the row address select. In fact, you know what? We can tell it's actually the RAS lines here, and the reason why is because there's DAC or DAC0, that's the DMA 0 signal, and that comes in, goes to this chip, and it also here as refresh gate, and it drives these little chips right here, these LS, I think it's an 06 or an 08, I think it's an 08, and yep, that goes to the RAS line. So the CAS lines, I think, well, actually, they're also connected to this DMA line right there. So either way, actually this line right here we should look at, that line we should look at, and then we should see activity on these signals all the time. So that would be the refresh part of the circuit I talked about, but we definitely need to have this working as well through this and that. And well, you know, like I said, just stuff has to be, it has to look like it's working correctly here. I don't know what it should look like for sure, but at least we should see some activity. Now, the other signal that was on the DRAM sheet was this one right here, which was XMEM write. I think it's like a write signal, and that comes in here. And yeah, this has to do with when the CPU needs to write to memory. This signal is generating this that goes to the RAM. Now, this is doing other things as well. IOW, this goes to like the IO ports for game controllers and serial ports and stuff like that. And MEMR is like a read signal. The thing is, this XMW, I'm pretty sure is used for the ISA bus, although maybe it's not. Actually, it might be these two. I can barely read this. It's XIOW and X something. I think sheet 11 is actually the ISA bus connector. Let's just quickly look at that. And yeah, XIOR, XIRW. So without those signals working correctly, we would not have a working CGA card at all. So that kind of implies that this chip is working okay. It's just the memory write signal, it could be problematic, or maybe it's not making its way to that LS245 correctly. But you see it's going to other things as well. And I think it's going to like other peripheral chips and things like that. In fact, let's look at page 3, which happens to be right here. And there's the signal right there, and it goes into this, and okay, this has to do with some chip select stuff here. I don't even know what that goes to, sheet 5, whatever. But those signals are also found here. There it is. This has to do with the DMA controller. So if those signals weren't looking good, then this wouldn't be set up correctly either. The DMA controller wouldn't be able to be set up. And I guess it goes to that chip right there, which is the one we replaced, and we're sort of suspicious of these signals. All right, so it doesn't go to that many things, but the thing is, it does go there, and we know that's suspicious, and it goes to the DMA controller, which was right here, and we know that that's kind of suspicious. And then obviously it goes over here to this refresh circuitry here, and we know that that's potentially suspicious as well. So I suppose we need to look into that. Now the question is, where's this chip on this motherboard? And it says U17. It's an LS, and I think it's a 243 there. It's kind of hard to read. Now, unfortunately, I don't immediately see that particular chip on here. So what I think I'm gonna do is I'm gonna use this, which is a little brush here. It allows me to quickly brush around the pins. And I know that that particular chip is connected to pin 1. So I have the multimeter on continuity mode. It's connected to pin 1. See, this little brush here is connected. A viewer sent this to me, and it's been very useful. There it is. It's this chip right here, which has the silkscreen markings quite worn off on it. I think yeah, it's right there. Well, I suppose actually it might not be that chip for sure. And the reason why I say that is because that signal goes to other things on the motherboard. It goes to several different things, but it seems to exist on here or in those vias right there. Well, it's on pin 6 on that chip, but according to the schematics, it's pin 5 that we're looking for here, this signal. So it's not that chip. I'm gonna keep poking around here. Let's just make sure we're still in continuity mode. We are. All right, I have had no luck finding this chip. Now it says LS243, pin 5. So I went and found a picture of the original motherboard, 74LS243. Pin 5 there on that IC is what generates that signal. Well, and for the life of me, well, this is where these diverge a little bit. This is the chip here, pin 1. That's the signal we're looking for. It's found over here on this 138. It's found over here on that chip, and that is an O2 and the 138. So this motherboard doesn't seem to have that particular chip that's mentioned in the schematic. So I guess there are differences here, and they are not just direct clones. That makes the troubleshooting step or process here a little more difficult. That was a bit of a dead end. So I think the next thing to do is we're gonna look at those signals that are driving that chip. I put a CGA card in here with the BIOS ROM chip. Why is it not even posting? I'm expecting to get the BIOS boot screen, and we're not. Oh, wait, what? So it's working, but not working? What is happening here? Actually, now I think about it, it's acting like it's warm booting here. Like it's not even giving us the option to run basic or anything like that. Okay, I'm confused. I actually don't really understand what's going on here. I know this BIOS has like a warm start mode where if you hit Control-Delete, for instance, you know, it doesn't give you the full RAM check again. It's like it's doing that right now. I just swapped over to another clone type BIOS here. Let's see what this one does. System already. RAM testing. Yeah, don't tell me that this motherboard has like fixed itself. No. Don't tell me that. That would be horrible. IBM compatible BIOS. No. So I'm gonna put the XT IDE card in, like that. I mean, come on. No, this is ridiculous. No, it's not gonna boot here because I have it set for like high memsys and things like that. Yeah, I think it freezes if you try to run it there. So I've put a floppy drive controller in. We're gonna take this BIOS off and we're gonna put in the diagnostic ROM, the one we were running in the first part. We're gonna see if this is still detecting RAM errors. If it's not, I don't even know what to do. I haven't done anything with this machine. After that first video, I just set this aside. Okay, here we go. I do have floppy drive connected as I mentioned. Oh no, look, bit errors. So there's issues, there are issues. So this is acting the same as the other one was, but we were literally booting into DOS with these errors. And look, it says every bit is bad down there. Well, it did. This thing is such a disaster. It is such a disaster. Now, in case you're wondering if there's a problem with this PC Turbo BIOS on this motherboard, I had been running this BIOS, this exact chip in here for a long time and never had any issues with this board. I mean, once the DMA problem was fixed, it was all working perfectly. Then we started having the RAM errors. Now when I put this in, it thinks there's a warm start and it just bypasses it and tries to boot DOS. This other BIOS, which I don't even know, this didn't come on this motherboard, it was from a different motherboard. This is that our system already BIOS, that seems to work. And now the diagnostic is definitely telling us that we have the same RAM problem we had before. And I don't know if this is actually frozen. It looks like it's doing some kind of a slow refresh test. I'm gonna hit the reset pins here, reboot the computer. Let's see if it's just acting just as bad. So it's setting up the DMA, by the way, and the parity error. That's what those 2 lines above were. Yeah, we're getting RAM errors exactly the same. So let's talk a little bit about how parity error works on a PC. From my understanding on these XTs, the circuitry that handles the parity error, that's the 9th RAM chip, what it does is if it ever detects anything's out of the ordinary, it triggers a non-maskable interrupt. So that's like an interrupt that's even higher than any of the other IRQs that are on the system. And when that is triggered, it will execute some code that it's in your ROM BIOS and it will say parity error and it has the address. What happens is, like, no matter what you're doing, it will reinitialize the video, print that message, and halt the system. Now on the PC Turbo BIOS, I think that's what happens. And maybe it has to continue, yes or no, but on the original XT BIOS, it doesn't let you continue at all. Now I'm wondering on this BIOS here, this is the this one with the system already, maybe it never even turns on the parity circuitry, because if you don't initialize it by setting up like the, I don't know, the 8255 there, then the parity error checking just won't be enabled at all on the XT. And maybe the entire problem is within that circuit. And when you don't enable it and you just let the system run without the parity operational, everything works. Because clearly this is turning on the parity, because you see at the bottom, in the bottom corner there, parity errors, and has a bunch of bit errors and stuff like that. So I'm wondering if somehow that's what's going on. Now with this PC Turbo BIOS, it's available on GitHub and you can edit the code. And I could go ahead and change the code on this to disable the parity error altogether, the parity checking. And then we could see if the system then works with the parity error disabled. That's the only thing I think that could be going on right now. Now, in case this system is flaky because there's a bad connection and pushing cards into the motherboard basically made it break when it was working, maybe I should put this system already BIOS back in here. I don't know what we would call this. I'm just going to call it system already and see if this thing can still boot the system as it sits right here, because it seems happy. Now this might be a garbage RAM test, which I'm pretty sure it is. The RAM test that's in the PC Turbo BIOS is not good. It's not going to catch a lot of problems. Look, it freaking just works. But I am going to hold down Shift now, and then we'll run check it. And we'll see if like this thing boots DOS normally. I mean, it's running DOS. It's in DOS. How could DOS work if the RAM was completely broken? It couldn't. Let's run check it. If check it runs, then it's got to be a parity error circuit problem, and that this particular BIOS does not enable parity error checking. That's the only thing I can think. Or it just ignores it altogether. Like if there's a non-maskable interrupts, then it just doesn't do anything at all. So we're going to test the memory here, and I'm going to change this to test all the RAM, none of that, and we're going to change quick test to no, which actually does like a more thorough RAM test. And you know what? It just froze. Yeah, the system just crashed. So that's not that's not reassuring at all. Gonna have to hit the hardware reset button there. I couldn't even control delete out of there. Now, as I mentioned, the RAM test with the PC Turbo BIOS is not good. It's very rudimentary. Working with a friend, with Dave, on improving that. This ROM BIOS might not be doing any kind of RAM checking whatsoever. And maybe it's just like printing a number and like literally doing nothing more. I couldn't tell you. But obviously, MS-DOS is running here. So we're going to try check it again. I'm just not going to try to change anything. I'm just going to run it as a quick test. If it starts, it is starting. Yeah, this is very shocking. All right, here we go again. I'm just going to run this pseudo-random I think it's frozen already. Oh, it's not frozen. I think what it does on the first pass is it has to check where Checkit is running itself, like it relocates itself, then it runs again. Because of course, MS-DOS is currently running, and you can't just test memory when you have stuff in there. You have to move things somewhere else temporarily and then run this test. MS-DOS is sort of sitting up at the top of memory and down at the bottom of memory. And obviously the program Checkit itself is in RAM too. So you have to kind of, it must be doing some kind of relocation stuff. Now, generally, if you turn off the quick test, it gives you a much more thorough RAM test. I think it's just doing like a pseudo-random one right now. I mean, it's going though. It hasn't stopped yet. Now, while this runs, let's talk about the parity error problem again, that maybe it's the parity error circuit. I don't think it's the parity error RAM chips because there are 4 of them. And if one of these went bad, we would only get parity errors, theoretically, in that particular bank of memory. So that's 256K. That's 512K or second 256K, and then we have 64 and 64. So to say this chip were bad, I mean, it passed. It's just wild. It would not be bad everywhere. We were getting random errors everywhere in RAM. I'm going to try to change that one more time to turn on that additional thorough testing here. So we hit change, we go through there, quick test, no. Okay, let us change it that time, so we'll let this run through now, and then we'll see what happens. So back to what I was saying. If there was a problem with like one of the parity chips, then it would only be, we'd have random errors in one bank, not all the memory. That's kind of why I think that there's a problem with the parity error circuit itself. Look, it's doing a walk bit now. Walk bits are interesting, so it writes patterns and it kind of alternates them back and forth. I don't think this is doing a march test specifically, and a march test is different because what it does is you write to all of memory, and then you read back everything one byte at a time, and then you invert it, write it back into the memory, go through the entire RAM, and then you do that again, but you start from the top and go to the bottom, go invert, 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 and then you read back the memory from the top down. And what happens is because you've gone through 2 inversion cycles, whatever pattern you started with should be left in the memory. And that catches all sorts of issues because what you're doing is you're not just writing a pattern and then reading back the pattern. You're writing a pattern, reading a pattern, inverting it, writing back what you read, and you're doing that twice. So if any kind of random bit errors are starting to creep up, or maybe you write or read from one cell and it writes to an adjacent cell, well, that's going to affect that read-write cycle. And when you go through that inversion process twice, what you're going to be left with is not what you started with. So if you fill it all with zeros and you do all that inversion twice, then when you should be done, it should be all zeros. That's why a march test is so great, because it catches all sorts of issues. But you do various patterns with your march test. You don't just write like all zeros and then invert. You might do AAs, which are alternating bits, or 5/5s, or other patterns like random patterns, and then you can just keep doing that inversion process over read, write, going back, forward. You catch page errors, you catch all sorts of cool issues that these types of memory tests may not catch. I don't know exactly what this is doing. It's not being very explicit, but march tests weren't really a thing early on in the 80s when I think this software was written, which is why nothing really uses it. But it is an excellent way to catch memory errors. And if using memtest86, I'm pretty sure that that is using march tests, among other types of tests as well. But it's slow because you're doing a whole lot of reading and writing and inversions and stuff like that. So it takes a long time, but it's just very thorough. Now, what I really hate about this RAM test here for Checkit is it doesn't give you any indication that it's not frozen right now. The flashing question marks you see at the top right of the screen, that's just the CGA card putting a flashing character attribute. So it'd be nice if there was like a little spinny thing that was actually being updated by the CPU while it was executing code, because right now it's been stuck on address lines for a while, and I don't know if that's correct or not. So anyways, I think what I'm going to do now is I'm going to pause the video to save battery on this camera because it seems to run out of battery all the time, and I probably need to buy a new battery for it. And then we'll see if this runs. I'll just let this sit here for a while and we'll see what happens. Well, I think this is frozen because it's been sitting here at pseudo-random and at the same address for quite a long time now. So while it was running, clearly it's not super reliable. I'll power off the system. I went ahead and I made a new ROM, and this was the Turbo XT or PC Turbo ROM here, and I modified it. I think I disabled the parity checking appropriately. It's not like there's an option in there that says disable parity checking. It's not that clear. I guess because generally people are like, why would you ever want to disable the parity checking? You should always keep that enabled. And let's power this up, see if it works. All right, parity checking disabled by Adrian. All right, so this is still getting system error number 2, which I did look up in the code itself, and system error number 2 is definitely a RAM error. So I don't know why the other copy of this one here, wasn't able to, I should just disable the RAM check altogether. I couldn't do that as well. There's actually an option to do that in here. Now I also changed it so it says Super XT BIOS instead of Turbo XT, because this is a non-turbo motherboard, so I just took the turbo code out. So I think what's going on with that other ROM, notice we're not getting parity errors. I think what's going on with that other ROM is that it doesn't enable parity checking, and it's such a terrible RAM test, or no RAM test at all, that this is actually catching RAM errors that the other one is not catching. Now I can just press Y to continue. Oh, parity error. So clearly I did not disable the parity error properly. Okay, back to the drawing board on that. All right, we're back for try number 2. I have the BIOS modified. I just took out the entire non-maskable interrupt handler, which handles, I think, errors from the Mathco processor, but also the whole parity error thing. If it gets called, it just returns, doing absolutely nothing. I also disabled the entire RAM check as well, and let's see what happens when we power this thing on. There it goes, zooming right through the RAM test. Now, I tested that before I tried it on the real hardware on an emulator, and it did a very similar thing, meaning I could see it counting up the RAM, but it doesn't actually do any of the RAM tests. That part is disabled entirely. Also, the system has frozen, so we certainly still do have problems on this machine. I'm just power cycling it here. We certainly have problems. Bypassing the RAM check oh, it's doing that thing again, where it thinks it's warm starting. I should have just modified the BIOS so it absolutely did a cold start every time. There's a little routine in there. I can't remember what it does to check to see if it should do a cold start or a warm start. And definitely when it's configured to warm start the system, it does not attempt to go into basic. There's another option for that. It's cool, this is assembly code. You can just go in there and edit it and reassemble and link the BIOS pretty easily. So I put a disk controller back in, so it might try to actually boot from the floppy disk. I know it's just off the edge of the camera there. I think what's happening here is to facilitate a warm start, it's looking for something in the RAM, some kind of a bit or something that's set. And I have a feeling that it takes a long time to decay. And if I just turn this off for a while, it's not actually booting off the floppy either. If I turn it off for a long enough time, then it should actually consider it a cold start when we first power on the machine. But RAM takes a bit of time to decay. There it is. No ROM basic. Basic is actually installed in this machine. You can see the chips are there, but it's trying to boot from a disk. And the system is not frozen. I can hit Control Delete there, and now it's doing a warm start. I think I'm doing that thing where I'm grasping at straws a little bit. I think what we've shown here, it keeps doing a warm boot. I think what I've shown though, is that if the parity checking is disabled or doesn't do anything, then the system does kind of start. But on the other hand, with this modified BIOS down here, it was still detecting RAM errors. Of course, it's not now because it's just, oh, there it goes. It's not checking the RAM any longer. But the system is not booting, right? It just kind of hangs. Kind of reminds me of another system we had that was doing this. But why does the system actually boot off my compact flash card when I use the system already BIOS? That's pretty curious. I put the system already BIOS back in there. Let's just see what happens with this now. Super fake RAM test that it's running. Clearly we know that's BS. This was probably installed in these clone motherboards so they could sell you machines that had sketchy or marginal RAM, things like that. And that way they could, get it out the door. So they just disabled those routines. Yeah, this actually boots. Very strange. That's super curious. I don't really get that. Just so we can see that this BIOS that I made does actually work, I put it into the motherboard here. That's got 256K, XT IDE, and CGA card is in. Oh, I gotta plug floppy keyboard in. Okay, there we go. And let's make sure I can press Shift to bypass DOS. And maybe there's something wrong with this BIOS. No, it's booting. So it really doesn't boot on that other motherboard. And look, the system is running now. Of course, this thing only has 256K of RAM, but you can disable parity checking entirely. And yes, PCs will still work even without this extra chip in here. Let's just see what happens if I remove the parity chip. That's an interesting test, actually. I've never done anything like this. Oh, that socket's a little bit damaged there. Okay, parity RAM chip has been removed entirely from the board. This system should still work. Well, of course, the RAM test doesn't work. I mean, it doesn't actually check anything, but the system still should be operating normally here without that parity chip installed. And I think it is. Yes, it is. There it is. We have a working system still without parity installed. So yeah, it's just totally disabled in this particular BIOS image. All right, well, I thought I had a smoking gun there, like that it was the parity circuit itself that was causing that other motherboard not to work, but that's definitely not the case. While the system is operating, if a parity error is detected by the parity checking circuit, non-maskable interrupt fires, and that runs that routine, which I deleted from this BIOS image, which clears the screen, prints the parity error at the top, does that kind of stuff, halts the system essentially. But if a regular RAM error is detected while the BIOS is just doing its standard RAM test, that's a completely separate routine. And while that can throw a parity error, which would create that parity error screen to come up, the regular system error number 2, which on this particular BIOS here, is just a RAM error. That's what gets called if it detects a RAM error during that initial power on RAM test. So the fact is, before I disabled, well, when I thought I disabled parity error checking on the Super XT BIOS, but I hadn't really, but I thought I had. The memory test was still in place and we were still getting normal RAM error, system error 2. That's just typical RAM errors. And then we were running check it on this machine and it was freezing up. So it kind of indicates there is definitely still an issue on this machine. Also, when I ran this XT diagnostic ROM here, the super soft one or whatever, it was detecting RAM errors as well. So I am actually no closer to figuring out what's wrong with the other motherboard there when it comes to the RAM errors than I was at the beginning of this video. I was really hoping for something to point me in the direction that would just give me an idea of what the problem was, but yeah, nothing. Now, I went and highlighted several things on these schematics to go check, and I haven't checked any of those things, right? We were gonna go look at those signals. I kind of got sidetracked trying to figure out the parity error stuff, especially because putting that one BIOS in this thing made it kind of work. Now, let's look at the schematics here for one moment. So this is the DRAM chips, including the parity RAM chip. Now, the parity RAM chip is read and written from this chip here, which is essentially designed to calculate parity. But all of its data lines, which are the inputs, is shared with the data line inputs on the RAM chips, and that all again goes back to this transceiver, the one that we've already replaced so we know is good. So this is going back to what I was talking about at the beginning of the video, where maybe the signals that drive this aren't good. Now let's look at them with the scope. I've sort of delayed this long enough. Let's just look at these 2 pins on here and see what they look like. Problem is, without a logic analyzer hooked up to all of that decoding logic on the other page, we're not gonna, if the signals look good, that's not gonna really tell us anything. But let's just see if these signals don't look good for some reason, and maybe that'll be, I don't know, it'll give us some kind of an indicator that there's a problem somewhere else. So according to the schematics, the 2 pins we're gonna look at are pin 1 and pin 19, and that's on the bus transceiver right here. And this is the scope that's connected. All right, so I'm on a random pin on the CPU. I just wanna make sure that this thing is showing us data or information correctly. So starting on pin 19, we see lots of activity, and pin 19, according to this, is the enable pin. So that there is that chip being enabled, which I'd say looks correct. And then what we're looking at here is pin 1, which, you know, it's kind of low, I suppose, 3.8 volts, 4 volts, but that should be good enough for TTL. Anything over like 0.8 or 1 volt is going to show up as high and enabled, which is what we want. We want it to come all the way down to ground and, you know, have a good looking signal. And that looks good. That is the direction signal, which is pin 1, which is this XM whatever signal right here. And the one that we were looking at before was this RAM address select line. And both of those look absolutely fine. Now, what I'm looking at here are the pins that face to the DRAM. And you see how, you know, you might think that looks weird because it's floating. Well, that might be actually okay because this chip is not enabled all the time and it's tri-state, which means sometimes the output is just floating. And when you float, you get this sort of stuff in the middle here, and that's completely fine. As long as we're getting stuff that goes all the way up to the top and all the way to the bottom, I'm gonna say that that looks okay. I'm just going through the various pins here, And, you know, that looks a little low, but I'm going to say that's probably totally fine. And same with these other ones here. Now, if we look at the other side of the chip, I just moved the video card so we could do that. This is the input. This is what's coming from the buffers and the latches and stuff that are on the CPU side. Everything there looks fine. There's no floating going on over here, but I would expect that. So this is kind of what I would have to expect. So anyhow, as I said, some of this just looks a little bit suspicious. That's the direction signal, so that's fine. Yeah, what's going on here? I wonder if we just have some bad chips on here. I mean, a whole bunch of them. I mean, these are AMT. I dismiss these as not being problematic, but I guess anything is possible. I don't know. All right, so on to the next thing to check. It's the DMA refresh stuff. I don't exactly know how this should look, so we might have to look at the other motherboard again, but it was this signal and that signal there, which are the two things that seem related. Now this thing right here is an S138, and that goes to there on pin 4. And then this one here goes into this all LS138. So I might need to just trace these back all the way to the DMA chip. It might be easier than trying to figure out which of these chips they are coming from. And if we look here on the DMA chip, pin 25, it goes to all the two signals we're looking for. One of them goes through that gate and the other one doesn't. Let's see what those look like on the scope. Okay, so that's the DMA controller here. It is the 37A, just double checking against schematics. Yes, it is. And let's turn this system on. My assumption is what we're looking at there is the refresh, which is enabled by the ROM BIOS. If I reboot the system, that should probably go away. And yep, see how it does? And then it comes back. So according to the schematics, this chip here is pin 3 and 4 on an LS04, and that's the other DMA refresh signal that goes through that. We need to check that. We have a 74 LS04 right here. If we look at pin 3 there, there's way too much activity. They might have moved it around. Ah, there it is. Okay, so it's on a different pin. So that's the output, and it looks good. Yeah, it inverts it. So the refresh for the DRAM does appear to be working fine without any issues. Now that isn't to say though that the DMA is not writing to the wrong place in memory. And again, it comes back to these chips. I already replaced this one previously. But if these aren't outputting the correct address lines, then theoretically it's possible that as this goes to refresh DRAM, well, this stuff that's coming out of here is not quite correct. Now that 670 chip is this one right here, and that is in the general vicinity of the corrosion, although I guess we're getting a little bit further away at this point. Now the problem is the outputs of the 670 here are these 4 address lines, is they're on the common address bus with the rest of the CPU. So it's hard to know when this is trying to drive the bus, if it is or not. And I am on pin 10, which is address line 16. And you know, we see all that activity there. Now the thing is the CPU generates address line 16 sometimes, and then that thing generates it at other times. Now you see how there are those low pulses? I'm pretty sure those coincide exactly with pin 25 here. See that pulse right there? So I wouldn't be surprised if that is somehow related. So all this activity in the middle of those pulses is actually coming from the CPU, and these pulses are coming from this chip. And we're on that signal, which looks just like that DMA 0 stack signal. That is a read signal, which is coming, it's driving that 244. It's also coming from a DMA enable signal over there. Boy, you really can't read that, can you? Coming from DNA enable. And I'm on this 244 on the far edge, and I'm pretty sure that's this one right here, which is all part of that same DMA circuit. And it's certainly getting enabled at the exact same time as everything else, along with the DRAM refresh. Now it's pretty much impossible to look at these outputs here and know that it's working correctly, because it's going to buses here that are shared with all sorts of other things. The address bus here goes to everything else, and then these XA signals here are also shared with a bunch of other things like the ROMs and things like that. So it's very difficult to know if this thing is actually working correctly just based on the way this all looks. And this is the side of this chip that's talking on the address lines directly, like where the CPU and stuff is. Well, these latches over here, and this is versus the XA lines like that. Look how you can see those pulses there from the DMA activity, which you would actually kind of expect. And that's because this is going to be accessing a lot of the address lines, not some of the ones at the very top, of course, because the DRAM ends at 640K. So it should be toggling. Although what's kind of hard to tell when we look at this here is those pulses, which we know are the DRAM refreshes, it should be toggling through all of the DRAM space, which is like 640K, right? But don't they just seem to not be doing anything at all? I don't know. It's really hard to tell, you know, amongst all that noise, so to speak. Now, it has me kind of thinking, this DRAM controller were not working properly, and it weren't like toggling through, ooh, it is very hot. That's interesting. If it weren't toggling through all the lines properly for the address lines for refreshing the DRAM, like it was just stuck. Even though this chip seems to be okay, like the diagnostic ROM says that it's fine or whatever, what if it's not actually sending those address lines correctly to refresh the RAM? And the RAM is what's decaying. Now this already happens to be in a socket, so I can just take that out. And I can take the one from the other machine, and we can just give this a quick test. Let's just see if things look any different here. Let's make sure that's in the right way. It is. Let's see if things look any different. I don't know. The system might be at a parity error anyways. I couldn't tell you if this looks different. I still see those pulses in there. Well, switching back to here, it's still got a RAM error. So yeah, it's not the DMA controller. This one gets warm as well. Same NEC part as on the other machine. All right, I switched back to the motherboard that works. And I think what I'm gonna do, because I'm completely stumped, I'm just gonna take all this RAM out of here and I'm gonna put it in this motherboard. That is my last ditch effort to try to figure out what's wrong with this. I really don't think it's the RAM. I think this is gonna transfer onto there. We'll have 640K, it's all gonna work perfectly. And I really feel there's a fault with some other chip on here, and I'm completely stumped and I have no idea what it might be. So I'm back, and I know I said I was gonna swap that ROM, but I decided to take a break. I go had dinner, and then I started editing up the video footage I had so far. And while reviewing that footage, I had a thought. Remember on the schematics, we had this chip here that I couldn't find. This was the LS243. And I started looking at the signals here, and I noticed that both the memory read and write and the I/O read and write go through this chip. And it's almost like an LS244, which is an 8-bit buffer, basically. It can be turned off and on, but it's only unidirectional. I think that's what's going on here because look, there's a DMA enable signal that turns off these signals, I guess, whenever DMA is turned on. And remember, on this motherboard, I was not able to find that chip. It doesn't seem to exist anywhere on here. But it got me thinking that this chip here, or a chip like it, has to exist on this board. And the reason why is because when DMA is enabled, these signals need to be turned off coming from the CPU because the DMA controller is going to take over those signals. I don't know if it drives them directly, but I know that the CPU should no longer be driving those signals anymore. So that's the reason that this chip is here. Now, when we look at these signals here, they go to sheet 1, and if we look at sheet 1, they're coming from this, the 8288. That was the chip at the very beginning of this video series that I suspected was the problem. This chip here actually generates those I/O and memory read-write signals, and they go off to this chip here, and they can be enabled or disabled before they go off to a bunch of different stuff like the DRAM circuit. Well, the one thing you might have noticed when I'm using the Turbo XT BIOS in the bad motherboard, which is down here on the floor, this one right here, do you notice that when it goes to list the peripherals that are installed in the board, it always seems to say that there's like a clock and some serial ports and stuff installed, which are clearly not on this board. But the motherboard that works, it doesn't show those additional peripherals. It just shows that there's a floppy controller if there is one, or if there's not, it just shows the CGA card and the 8088 processor, and that is it. Well, that got me thinking all of a sudden, what if the chip that is connecting those signals through from the 8288 chip, the one that generates those signals, to the DRAM and to other stuff, what if that chip's bad and say it's always on, like it's not being turned off when the DMA enable signal is telling it to turn itself off? When a memory read is coming through, it's going through to the I/O ports, or the DMA is active and it's not disabling those signals that go to the I/O ports, which is why they're showing up as active. Now on the PC motherboard, there are all sorts of other things on I/O ports as well, and generally everything seems to be working properly. But remember, the DRAM also mostly works properly because with that other BIOS chip, we were actually able to kind of get booted into DOS. The system was just a little bit unstable. But what if that chip that's replacing the 243 here on the XT is somehow bad or marginally bad and causing those issues. That's the only thing I can think of, because we shouldn't be seeing a clock in a serial port unless that chip is bad and it's activating when it shouldn't. So when the BIOS goes to talk to the serial port to see if it's there, which is how it probes to see if it should list that, and maybe it's getting back some kind of data, which clearly it shouldn't because there is no actual serial port or clock on this machine. Maybe it's coming back and reading part of RAM when it should be reading an IO port, something like that. So I think I need to go search for whatever chip is connected to the 8288 here, because I should be able to tell it goes from this to whatever that chip is, the LS243 replacement on here, and then we should swap it. That's the only thing I can think. All right, and I did some probing around on the working motherboard here, because it's the same as the other one anyways, and I figured it out. It's this chip right here. This is the chip that is actually replacing that 243. It's this LS245. Kind of strange, but maybe they just had a lot of those and that's just the design they decided to have. So the outputs of this chip here end up on the far side of that right there. And there are 4 signals. There's the other one there. There's 2 on this side for the IO ports, I think, and 2 on that side for the memory. And all 4 of those make their way over to this side of this chip. Now switch back to the motherboard that has the problems, and it would be this chip right here. Now all we need to do is take a look at the direction or enable pin. Now I noticed that one of those 2 pins is actually hooked up to ground, so that means it's always on. So it's gonna be pin 1. You can see the trace going off there. That is the relevant pin that is controlling whether this is on. I'm assuming that's gonna be the DMA enable signal. So the non-working system has the BIOS in it. Let's put this on pin 1 here. Scope, let's take a look what happens when we turn it on. There it is. There's that DMA enable signal. That is exactly what we thought should be happening. Now we take a look at pin 1. We can see DMA enable. We go to pin 2. Not really much happening there. Pin 3 has the same signal. And the output of pin 2 is this one here. Okay, it looks the same. And then that one there would go to this pin, kind of wavering, which is interesting. And then this one here just has that signal visible and it looks as expected. And that pin there, in and out, kind of looks, I'd say, correct. And then I don't know what the rest of this chip is doing. In fact, I'm not sure it's doing anything. I don't see any signals going to anything on there. So I think this chip is only using the 4 inputs on the top and the other 4 are just wasted. Now my problem is I don't really know what signals are supposed to look like on that chip. But luckily we have a working motherboard. So I'm gonna put the same BIOS in there and we can take a look. So there's the DMA enable signal on pin 1. Well, look at that. That is pin 2. These pins don't look anything like the pins did on the other motherboard. So that just has nothing on it. That has stuff happening on it. That is not at all what we saw on the other motherboard. So I almost feel like on the other one, what's happening is that input pin is maybe getting replicated onto all the other ones? I don't know, I'm not really sure. Let's swap back to the bad one just to double check. This honestly feels like the first concrete thing I've found in this entire troubleshooting exercise. And if this turns out to be what's actually wrong with this, I'm gonna kick myself because the whole time the symptom was sitting there right in my face showing that it had erroneous stuff on there. So let's look at the output again on here. Okay, hold on a second. Now we're getting stuff on the output of that chip. Let's look again. Okay, so DMA enable, there it is. I guess the system was just frozen. So that there looks more normal. The output of that should be that pin. Then we have this to that. That looks okay. Those 2 pins don't have anything on them. And that one there just has the DMA enable signal on it. And it looks like that. I don't remember if I saw that on the other motherboard. So now that I went back and tried this again with the system actually booting, the outputs and inputs on this look okay now. They don't look like they're bad. In case you're wondering, I'm using the 8288 that's from the working motherboard, and the working motherboard has that scratched up chip, the one I found in my spare parts, that I initially thought was bad that I had tried on this. I never swapped back, so this is a nice clean one that was from the other motherboard. So I don't think that's the problem. I still feel that that chip may somehow be problematic. it just sort of explains a little bit more about what's going on. If those signals are getting turned on at the wrong time, the IO signals and the MEM signals, then RAM is going to get corrupted and the IO address stuff is not going to work quite right either. It's just going to be all over the place. So it won't take me long to swap this out. So let me just do that now. All right, socket is installed. There's the chip I took out of the board. Here's another chip that basically is the same exact Hitachi part. Let's pop that in there. How confident am I that this is actually going to fix the board? Not very, but let's see what happens. Wow, system's not even posting. Yeah, I freaking made it worse. Well, I guess I don't really, oh, there's a missing chip right here. Let's put this chip back in there. Maybe now it'll work. Nope. Oh, okay. Nah, okay. It made zero freaking difference. Zero difference. Obviously, it goes without saying, if I take this chip out here, the system will not post at all. Yes, and it will not. So I'm just going to reinstall the original chip that I took out of this board, which obviously will result in identical behavior. Yep. And if we just take a look at pin 1, there it is, DMA enable. And now we should have, yeah, okay. That looks exactly like the activity on the other motherboard. And it wasn't working because I didn't have this chip installed originally. Dope, as Homer would say. All right, I thought I was going to be clever by thinking through the problem, and that clearly got me nowhere. So I guess I'm going to go back to what I was going to do before and swap all the RAM chips from this board over to the other one. All right, it is the next day, and I've gone ahead and I swapped the RAM chips, and these are the two boards. This is the non-working one, and it now has 256K that I took from the other motherboard. And the motherboard that has been working the entire time has the full 640K taken directly from the non-working motherboard. I also took those masking tape labels and made proper ones for the basic ROMs, and the PC Turbo BIOS is in here, and I currently do have a VGA card in there, but this has been running Check-It for probably 6 hours, and it's been running the continuous full memory check, and there's been absolutely no problems whatsoever. So that pretty much tells us that all of the RAM that was on the other motherboard here is perfectly good and has no issues whatsoever. And well, the working motherboard is continuing to work, and I guess this non-working motherboard here is the problem. So we're gonna swap back to the non-working motherboard now that it's got 256K on it, and we'll just verify that it still has those same issues with this known good memory. Power this on. Now I'm using VGA as opposed to CGA. Okay, there we go. It's counting up the memory. It didn't give us an error. But can we boot the system though? I'm gonna hold down Shift on the keyboard. Well, it's freaking working now? You gotta be kidding me. This is ridiculous. Now it doesn't see the basic ROM, so that's a bit interesting. I wonder if one of these is come out of the board a little bit or something. I'm not too sure about that. Okay, the only thing I can think to do is let's go back to the CGA card in case somehow the CGA card causes an issue. All right, we are switched back to CGA. And tell me. No. I mean, I don't get why he doesn't see basic, but why does it work now? I don't know what's going on here. I really don't know what's going on. The system is booting. Or no, yep, there it goes. What the heck? Of course, we're only got 256K of RAM, but why is it working? Why? The memory that's on the working motherboard, the one I was just running that memory test on, I moved the chips 1 to 1, so they're in the same exact positions even on here. And this thing never had a problem. It just worked right off the bat. It booted right up. It ran that RAM check for hours and hours with no issues. But with this RAM, when it was in this board, it just refused to work. But the RAM that was on here, now that it's in there, it's working. I just don't get what is freaking going on here. So while I was moving the 256K off the non-working board onto this one, I noticed a little difference here that I'd never noticed before. There's a jumper there that says on for 640K and off for 256K. And this is a jumper that goes into the PAL here. I thought the PAL was just for the ROM mapping, but I guess it does have something to do with the memory as well. And interestingly enough, if you remove this jumper, what happens is, even when you have 256K chips installed, like these first two banks, it treats all of the memory as 64K, which means that you have a total of 256K. Now, I took a look at the non-working board, and it doesn't really have that spot for that jumper, but you see those 4 pads right there? Those are jumpers that go to the PAL chip, and I verified using the multimeter, those top 2 pins go to the same 2 pins on that PAL as the jumper does on this motherboard. And currently the top 2 pins are connected together via a trace. But if I cut that trace and installed a pin header there, that would actually enable those 2 different modes on this motherboard. Perhaps this option was there originally, but it was sort of removed from this spin of the board, which says Rev 2D there, was because 64K RAM chips were much cheaper and 256 were unaffordable at the beginning. So they just wanted people to have the option to run all 64K chips in their system. And then later they could put the jumper in there and then they could run the 256K. But maybe by the time they spun this revision, they never thought anyone would ever want to have only 64K banks of memory, and they would want to have 640K total, which is 2 512K banks here, hence the jumper that is permanently enabled with that trace there. I don't know what those 3 other traces do. They go to other pins on the PAL, and this one doesn't even have those at all. It has these jumpers over here and here, which are installed, pin headers at least. You can kind of see that one down there. I think those are for changing these from 2764s to 27128s. You can see right there that it says 64/128K ROMs. I put the XT diagnostic ROM back in the non-working motherboard that has 256K, and let's just see if this detects any memory errors now as it goes through its memory test. Well, one thing that's interesting is it tested the CGA memory. It left a bit of junk behind. Oh, okay, look. It is detecting failing bits. The RAM that was on this motherboard had been on there since I got it. I never installed that MT memory or any of that stuff that was on there. And this motherboard for a long time had been working. I've used this motherboard for plenty of testing over the years without any issues. It just suddenly started having those random RAM errors all over the DRAM. And of course, with the RAM installed in this motherboard, which is essentially an identical motherboard, except for like some tiny little changes, freaking works in this one. But then the Motorola 256 kilobit RAM that was on the working motherboard when it's on here now seems to work. And there we go. Yeah, all the RAM tests have passed. I think the only thing left to do is install another 256K of RAM onto this board, so at least we can go with 512. And let's just see if adding another bank causes issues. Okay, an extra bank of RAM is installed. I set switch 3 off to say there are 2 banks there, so 512 total. I've gone back to my PC Turbo BIOS. Let's just see if this can count up 512K correctly here without giving us RAM errors. Parity error, and it's telling us the parity error is at 6F too, which is down in that lower bank. Let's reset the computer. So it was working fine with 1 bank, and now with multiple banks, issues. Was that the same parity error address we had before, 2F? Let's reboot one more time. All right, no, that's a different parity error address. And that's still down the lower bank of memory, but it's, okay, look at that. It gave us a parity error immediately. So it really feels like as soon as I installed that second bank of memory, it's taken out the entire system. Yeah, look, it won't even, it won't even post at all anymore. So it's like degraded so badly. Now the one difference is, look at that, I can't get past the parity errors. Why don't we put back the VGA card? It seems to somehow be working a bit better with VGA. All right, here we go with VGA as opposed to CGA. Wouldn't this be hilarious if that was the problem? No, okay, just making sure. I'm just making sure. So it is fascinating that with 256K, system was working, and now it's back to its old tricks again. Now, the one thing it hasn't said is system error 2 in that lower part of the memory. Well, I mean, we're getting those parity errors all super low though. That's not even a valid error code. If you look in the ROM BIOS code, that's not even possible. Problem is the ROM BIOS is actually using the main memory for parts of its routines and stuff, at least once it initializes the screen and writes this text on it. Therefore, if it's having RAM errors, you can't really trust anything that it's telling us here any longer because it's not running this code directly out of ROM. I mean, it is for the most part, but it's definitely using RAM for stack and stuff like that. So that's probably why that failed. And look, it failed at 112K, which is below the 256K boundary that would be for this second bank of chips. So I'm going to try something. I'm going to cut the trace between those 2 pins there. I'll put some pin headers on so I can install a jumper. That'll turn this 512K of RAM down into 128K of RAM. And let's see if, well, it counts up that memory at least configured that way. And by the way, as a refresher, I did try the PAL chip from this motherboard on here. I swapped them and it made no difference. It was still just as broken. So for cutting through traces, I use something like this, which is a little engraving tool. I absolutely love this thing for this purpose. That made super quick work of that. It's much easier than using a knife because it's hard to be precise with that. We should have 128K now. There we go. It also didn't have any problems with the RAM. It did freeze booting into DOS though, but it's possible that DOS needs more than 128K of RAM. I'm gonna power cycle the computer. Oh, parity error. Okay, no difference. It's just as broken as it was. Okay, jumper block has been installed. I did try these other jumpers here. They don't really seem to do anything that's obvious. In fact, if that's on there, 256K banks is on there, so 512K total, and I put a jumper on there, this counts up to 256K and then it stops. And it just sort of freezes at that point. But I can definitely say that with this jumper installed and we're using 512K banks and the second bank installed, this motherboard behaves, well, exactly like it was doing before. Sometimes it counts up to 512K, other times it gives an error right away. It's sort of all over the place, parity error there. Now, if we think about the symptoms of adding a second bank and that causes the motherboard to stop working, it sort of implies that the buffers and transceivers that talk to the DRAM are the issue. Well, we already know that it's not the LS245 because I already swapped that out. Well, I put a socket in, we tried a different one. It didn't make a difference. So the only thing that's left are the address multiplexers that generate the column and row address signals that go to the DRAM. Maybe putting that second bank in there is causing some kind of noise on some of those lines. So what I was looking for is any kind of signals that don't seem to be looking correct. Like say they were only going up halfway, something like that. I suppose the only one that looks a little bit sketchy is this pin 13, and that looks like that DMA refresh signal, right? I don't really see that in all the rest of this stuff. I guess maybe we can kind of make it out in this pattern a little bit. Oh, and that one as well, it's got it. So we're back on the working motherboard so we can take a look to see if things look different. So that's 5, 7, 8, 9, 10, 11, 12. And we're back on the problem motherboard. Yeah, I don't really see anything that looks out of the ordinary. It looks pretty much the same. I mean, I think this is the only one that looks a bit different, but the big difference is that the other motherboard wasn't giving us a parity error, which this one probably is. So when I power cycle this, you know, there's a lot more activity there that looks a lot more normal. Like I said, if we were getting signals that only came up to like here, and then they never went all the way up, or maybe they never went all the way down to ground, that would be something that we might consider a problem. And then we could look for those LS138s on here that generate those signals and think that those were the problem. Now, I guess part of the issue is though, of course, there's a lot of activity happening here. And I've seen those multiplexers fail in weird ways where they're still generating what looks like good signals, but yet it's not correct. And I called them 138s, but they're actually 158s. All right, well, I think I've isolated that these are the two multiplexers that handle the DRAM multiplexing along with these resistors right here. And these chips right here are what generate those signals, and then they output the multiplexed RAM address signals. And over here, same thing. So I am still just as stumped with this motherboard as I was before. We saw that one bank of RAM seems to work because we actually booted into DOS. 2 banks of RAM stops working. Well, I've done a lot of grasping at straws on this motherboard, and I could just keep going basically forever trying to keep swapping chips until we get to the bottom of what's wrong with it. I think for now, I need to take a little bit of a break from this thing. I've spent a lot of time trying to get this working, and as you can see, I've had pretty much no success. This is the working motherboard, and at the beginning of the video series, I'm pretty sure it was having a weird problem where it stopped counting at 128K, and I think it was because one of the pins on the CPU was bent over, and it was making occasional contact with the CPU socket. Once I took it out and I realized the mistake, I put it back in, and that seemed to have fixed the problem for good. Now this all started because I thought this 8288 chip which was on the other motherboard, the one that wasn't working, was not working. But as we know, the one that I first started with that was causing issues on the other one wasn't really, because this is the chip right here, the scratched up chip, and it's working perfectly on this motherboard as well. So that was absolutely a red herring that made me think it was this chip that was bad, when in reality there was some other fault, obviously, with the motherboard. Now, I had mentioned in the first part, I had gone ahead and ordered 5 more of these from eBay, and these just came. So I'm gonna add a little bit of bonus content at the end of the outro of me testing these, and I'll use this working motherboard just to see if these chips actually work. I'm kind of skeptical, but we'll see. It was about $11 ship for these 5 chips. So watch past the outro if you want to see me testing those. As far as the non-working motherboard goes, I am blown away with how many RAM issues I've been having lately with these PC things, because look, here's that RAM card that I tested on the main channel. And funny is, when you look at the symptoms of what this RAM card was doing versus what this were doing, basically the same thing. Random RAM errors, and you just cannot get a reliable and working system. I seem to have had really bad luck lately with RAM errors, at least on PC stuff. Now, at least the one saving grace is that Macintosh 512K motherboard, which also had RAM errors, I was able to figure out the problem with that thing and get that working. But it feels like PC architecture is just a little bit more complicated than maybe my brain can wrap itself around. And I just can't figure out and get to the bottom of what's wrong, well, with that motherboard down there, or that RAM card for that matter. So I'd love any input you have on what you think might be wrong with this and where I've gone wrong with my diagnosing of this issue. And I would like to get that motherboard working if possible, but I suppose if I can't, it's not the end of the world. It can just become a spare parts motherboard to fix other PC XT motherboards, I guess. Anyhow, I think that's going to be it for this video. If you liked it, thumbs up would be really appreciated. Huge thanks to my patrons. Their names are scrolling on the side of the screen over here. They make it possible I do this full time. So huge thanks to them. You can become a supporter with the link in the description below. You can get early access to videos and behind the scenes content, stuff like that, and just help me out. And so I think that's going to be that. Subscribe, all the other YouTube junk, and stay healthy, stay safe, and I'll see you next time. Bye. All right, it's now time for the bonus content. Let's see if these chips I bought from eBay actually work or if they're fake junk. So on this motherboard here, the chip that we're going to be replacing is this one right here, and that is a bus controller IC. Essentially, as we saw earlier on in this series, we'll find some scissors, it actually generates various signals like the memory read and write signal and the I/O read and write signal and things like that. It's essential for operation of the computer. If you take this chip out of the motherboard, you're going to get a completely non-functional motherboard. So this is really an essential part. And here are the parts I got. I think it just said 82C88. It didn't say what brand it was going to be. Oki Japan. I mean, I don't know if that's 57 week 1992. If that is, that's possible. Because, I mean, they still were making XTs at that point. These look... Oh, look, does this actually say Japan there? It does. That's cool. Maybe these are legit. I don't know. Now, these all have exactly the same markings on them. But maybe they all came from the same batch or whatever. So it's not really a problem. Now, the one on this motherboard here is an Intel part that I had in my spare parts. It's very scratched up, and it gets very hot while it's operating, from 1979, although that's probably not the date code, just the copyright date. I can't discern an actual date code on this chip. Oh, here we go, 1983, 48th week. All right, made in Malaysia. So I'll just straighten the pins out, make it a little easier to get into the socket. It's the right number of pins at least, so that's something. And let's power up the system. If this chip is bad or fake, the computer is not going to do anything at all. And it's not doing anything. Oh, it's working. Oh, wow. I actually really felt that it was fake and not going to work. So, well, that's exciting. It's not fake. So this machine has 640K. This is the working one. I am going to draw a tick mark on here. Well, I'll do it afterwards. Cool. So this is actually working. Now, it's funny. I thought it would have gone into basic. I don't know what happened there. So I have the XT IDE in here. Let's plug in the keyboard as well. I don't need to push shift actually, because the XT IDE is configured for the XT right now. The one last thing that's wrong with this particular motherboard is this connector is broken. So ideally I should change that. Sweet. Okay, well, the system absolutely worked. This bodes well. Usually if one of these is not fake, they're all actually going to work, and that's cool. And I would say that these are absolutely new old stock chips here. They look absolutely perfect. The second one is in the board. Power on the system. Are we going to get that flashing cursor? Yes. There we go. It works. Now it goes without saying, I didn't actually need 5 of these chips. The reason why I picked up 5 was because I think there was a bunch of sellers where they had 1 for like $7 or $8. And I thought, that's silly. Like, there's no point to buy 1, because what if it is bad or fake or whatever? So I just bought the 5-pack for a little bit more money. I'm just writing a check mark on here so I don't forget. I don't want to mix up the ones I haven't tested versus tested. Okay, that works. Anyhow, as I was saying, sometimes it's just better to buy the multi-packs. With these chips, they weren't tested. Like, I think it said new old stock. You can never really trust that. This did come from China. The thing is, you can't always assume that means it works, because it could actually fail. Even if they weren't fake parts, it can fail just sitting on a shelf, right? This stuff is, oh, by the way, incidentally, sometimes even the good motherboard shows that it has a clock and serial port and stuff. So I thought that might have been a problem on the other motherboard that was like an indicator of an issue, but it seems that the BIOS just does that even with this one. Anyhow, as I said, these chips can go bad sitting on a shelf, and even being new old stock, it's not like they were tested. So you might as well buy multiple. That way, if one is bad, even legitimately bad, it's not fake, well, that way you have a backup. But also, I just have a hard time spending like $8 on one chip when I can spend just a little bit more money and get a bunch of extra chips, just in case I ever need another one of these as spares. All right, and this is the last one, and it's absolutely working. Sweet. So I went back to the original Intel part, just because, and it's working as well. So I think that's gonna be it for the bonus content. I got good chips, but I didn't even need them in the end because I ended up having a spare that worked anyways. And the problem was somewhere else on the motherboard, and I just can't figure it out. So that's gonna be it for this video. Thanks for watching the bonus content. Bye.